Hello there, and welcome back to the Science Sleepy Minds. Tonight, you're lying under a blanket of ancient energy, not metaphorically, literally. Every pinprick of light overhead is an old message, fired across unimaginable gulfs of time and space, just to land in your eyes while you stare at the ceiling trying not to check your phone again. That pale shimmer from Vega, it started its journey 25 years ago. The red glow of Betelgeuse. You're seeing light that left before many of us were born. And the Andromeda Galaxy. That soft fuzzball is beaming starlight your way that set out, while early humans were still figuring out how to not die of soup poisoning. It's gorgeous, it's romantic, it's also wildly unsettling, because you're not just looking across space, you're peering through time itself. That starlight took the long way around to get to you, dodging cosmic dust, solar wind, and probably the occasional rogue planet. You probably won't survive the next 10 billion years, but that glow from a blue giant just might. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Let me know where you're watching from and what time it is. I love seeing how far this light reaches. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You blink and the journey begins. Somewhere above you, the light from a star finally finds its mark. Not just any light. This is a photon that's been on the run for millions of years. You're not its first target. It's passed asteroids, missed moons, zipped past gas clouds like a polite tourist refusing to stop for photos. But tonight, for some reason, it finds you. It's hard to appreciate just how small you are until you realize how big a distance starlight has to cross. Take Proxima Centauri, for example, the closest star to us after the Sun. Even that's over 4 light-years away. That's 25 trillion miles. If you tried to drive there at highway speeds, you'd arrive around the time Earth is swallowed by the Sun. Hope you brought snacks. Starlight isn't fast, it's the fastest. Photons travel at the ultimate speed limit, about 186,000 miles per second. And yet, even at that breakneck pace, the universe is so absurdly big that light still takes ages to get anywhere interesting. If a photon is lucky, it gets noticed. Most just fade silently into rocks, ice, or the backs of your eyelids while you dream about sandwiches. There's something deeply soothing in realizing the light you see tonight might have started traveling before there were pyramids, poetry, or pigeons. It's cosmic déjà vu, the universe sending postcards from its past. Now picture this, it's 100 million years ago. Dinosaurs snort and stomp across a steaming Earth. Somewhere out in the galaxy, a blue-white star burns hot and fast, unaware that one day, a tiny primate with anxiety and access to oat milk lattes will lie in bed and admire its glow. That photon it left back then. It didn't slow down, didn't get lost, and tonight it slips through your atmosphere, through your window, maybe bounces off your bookshelf and brushes against your cornea. One photon, one whisper of ancient fire. Historians still argue whether early humans understood the stars as distant suns or thought they were just holes punched in a sky curtain. Honestly, both sound equally poetic, but whatever they believed, they saw the same lights you do, faint messengers from the void. Now here's your quirky fringe fact of the night. There's a tiny chance, infinitesimal really, that the photon reaching you now has never interacted with anything since the moment it left its star. Not a speck of dust, not a molecule of gas. Untouched, unbent, pure. A ghost light loyal only to the vacuum of space. And yet, catch this, starlight isn't just drifting aimlessly. It aims. Your eyes are designed to catch it. Your retinas absorb those photons and fire tiny electric messages to your brain, where all of it, color, brightness, shape, gets turned into an experience. You're not just looking at light, you're decoding cosmic memory. Sometimes, when you stare up long enough, you'll see one star twinkle a little brighter, a little differently. It might be a variable star, or a distant flare, or just your eyelid doing that thing again. But in that moment, you're part of a ritual that's older than language. Reading the light of the sky, feeling small in the best possible way. Do stars care if you notice? Not likely. They burn for billions of years with or without applause, but the light they shed, it's generous. It shares stories if you know how to listen. A red star's light tells you it's cooler, maybe older. A bright blue star says it's burning out fast, living wild and dying young. And the dimmest pinprick might be a galaxy crammed with billions of suns, just too far to blaze any brighter. So tonight, as you lie there listening to your fan hum and your thoughts slow down, let your mind wander outward, past the ceiling, past the clouds, past the atmosphere and all its flickering satellites. Drift out toward the source of that light. Follow the beam backwards, tracing it starward until you're floating beside a star that doesn't even know Earth exists. Imagine what it sees. Not much, probably, just darkness. A few companions, maybe a passing comet every 100 years, but it shines anyway. It radiates, sending light in every direction endlessly like a lighthouse nobody asked for but everyone secretly needs. And of all the trillions of directions it cast its glow, a few rays made it here. Tonight, to your sleepy, curious, starlit self. You let yourself drift now, past the comfort of your bed, past the slow thrum of your home and deeper into space, pulled toward the places where stars begin, their dusty, quiet cradles. These are the star nurseries, nebulae, giant clouds of gas and cosmic debris, light years wide, floating through the Milky Way like forgotten thoughts. And you're gliding through them weightless, the dust not gritty but velvet soft. The temperature almost meaningless because here, time and matter are more important than warmth. The Orion Nebula welcomes you first. It's bold, colorful, always doing the most. If the galaxy were a high school, Orion would definitely be that one art kid who wears a cape and speaks in riddles. You hover within it, light slipping softly between tangled filaments of gas. Hydrogen dominates the air here, although air is kind of generous. It's mostly vacuum, but within this vacuum, gravity is stirring. That's the quiet beginning of a star, gravity gently tugging scattered atoms closer together. No big bangs, no sparkly poofs, just a silent collapse. At first, these clouds barely notice. They've existed for millions of years in peaceful disorder. But over time, mass gathers, and what was once a formless cloud becomes something denser, something heavier, something warmer. Historians still argue whether ancient civilizations suspected stars were born like this, slowly, from darkness, rather than from divine command. Some early mythologies did hint at it. Gods crafting stars from breath or clay, shaping them from raw material rather than conjuring them fully formed. Honestly, not a terrible metaphor for gravity's slow, meticulous handiwork. Now here's a quirky bit. The Eagle Nebula, home of those dramatic pillars of creation you've probably seen as a desktop wallpaper, those pillars are already gone, destroyed by a supernova thousands of years ago. But because the light from that destruction hasn't reached Earth yet, we still see them ghost-like, preserved in transit. The stars that formed there, already free, already lighting up other corners of the galaxy. You float deeper. Around you, small pockets of gas collapse tighter, forming what's called protostars, tiny hot blobs not yet worthy of the name star. They're awkward teenagers of the cosmos, caught somewhere between gas ball and thermonuclear diva. They're invisible to your eyes, but infrared reveals their heat, glowing faintly like embers under ash. You pause beside one, let's call it Proto-Bob. Bob's got ambition. The more gas it gathers, the hotter its center becomes. Temperatures climb. Pressure builds. At some point, the hydrogen atoms in Bob's core begin to crash together with enough force to stick. That's nuclear fusion. That's when Bob becomes a star. But we're getting ahead of ourselves. Right now, Bob's just spinning. Gravity has pulled gas into a disk around him, where future planets might be born. You drift near the edges of this disk, and there are whispers of what's to come. Ice grains, carbon chains, maybe even amino acid precursors clumping in the dark. Life in the absolute baby phase. Less crawling, more chemically wobbling. Not all of these protostars will make it. Some collapse too fast, flare too hot, and tear themselves apart. Others never gather enough mass to ignite, fizzling out as brown dwarfs, failed stars that simmer quietly, glowing in infrared, forever wondering what could have been. Space is dramatic like that. Stardom is not guaranteed. Back in your own corner of the galaxy, the sun was once just another protostar like Bob. About 4.6 billion years ago, it sparked to life in a similar nebula, maybe not far from where the Orion Nebula is now. It probably had siblings, other stars born from the same cloud. But over the millennia, they drifted apart, each taking their own gravitational path. It's like a family group chat where everyone eventually goes silent, except for that one cousin who still sends memes. You glide now past a tight little cluster of young stars, bright and blue and unbearably hot. These are O-type stars, real overachievers. They live fast, burn through their fuel in a few million years, and then explode in supernovae. Most stars are more chill, like your sun, just average, mid-sized, emotionally stable. But these giants light up their surroundings, sculpting nearby clouds into bizarre shapes with their intense radiation. It's like cosmic gardening, but with UV death rays. Still, their light is stunning. You pass near one and feel not heat exactly, but presence. Its glow is a pressure, a pulse. It radiates purpose. You don't need to speak star to understand its message. I am here and I burn, and that is enough. The nebula around you hums with this shared message. All around, tiny suns are waking up. Some will host planets. Fewer still may host life. But for now, it's enough that they exist. Born from gas and time and gravity, and already sending light into the dark. You float backward a little, taking it all in. What looked like chaos from afar, the ragged gas, the glowing knots, the strange shadows, now feels like choreography. There's rhythm here, a slow dance, and every star that is born adds another beat to the music. Out in the distance, something catches your eye, a different kind of glow, warmer, pulsing. A protostar on the edge of ignition. You feel the gravity, the pressure. It's about to become real. You hover nearby as its core begins to compress, and the temperature climbs past 10 million degrees. Suddenly, silently, it happens. The hydrogen in its center fuses. Energy erupts outward, perfectly balanced against the weight of collapse. The battle between gravity and fusion reaches equilibrium. It is now officially a star. And just like that, its light begins its long journey. One beam at a time, from the center outward into the future. You linger now near that newborn star, watching as it finds its balance, a calm but fiery sort of peace. It has finally earned its status, a main sequence star. The fusion reaction that now burns in its core is what makes it shine, what gives it energy, and what keeps it from collapsing in on itself. You hover just beyond the edge of its intense brilliance, marveling at how something so furious can also be so steady. This is where it gets good. Deep inside this star's core, atoms are dancing the most dangerous and beautiful dance in the universe. Hydrogen, the lightest, most abundant element out there, is being squeezed and smashed under immense pressure. Each time 4 hydrogen nuclei collide in just the right way, they fuse to become a helium nucleus. But here's the twist. The resulting helium weighs just a little less than the 4 hydrogen atoms that made it. So, where did that missing mass go? Well, surprise, it didn't disappear. It turned into energy. You know the equation already, the one that sits quietly on high school physics posters like it's no big deal. E equals mc2. Mass becomes energy, not metaphorically, not spiritually, literally. That tiny bit of lost mass explodes into pure energy and helps power the star's glow. A fusion fire so efficient, it would make your microwave weep in shame. The energy from this reaction pushes outward against gravity, which is always trying to collapse the star inward. It's a perfect tug of war. If fusion ever stops, gravity wins, and that's how stars eventually die. But not yet. This baby's just getting started. Historians still argue whether the ancient Greek philosophers had any real clue what powered the stars. Some, like Anaximander and Heraclitus, thought stars were just holes in a rotating crystal sphere. Others imagined them as burning stones. Honestly, considering they didn't have telescopes, not bad guesses. But the real mechanism, the fusion of light elements under pressure, was a secret the stars kept for billions of years. You drift closer to the core, knowing full well you shouldn't. The conditions down there are beyond lethal. We're talking over 15 million degrees Celsius. The pressure is so immense that if you stood there, somehow, every atom in your body would be crushed into plasma pudding before you could say, "Bad idea." But you don't need to be safe. You're just consciousness now. Sleepy, star-curious consciousness. So you drift into the core, past the helium bubbles, past the writhing plasma, to the very heart of the machine. This is where light is born. A photon is created, just a tiny packet of energy, the smallest quantized bit of light. It begins its escape but immediately smacks into another particle. That's how it works in a stellar core. Photons are generated constantly, but they don't zoom out in a straight line. No, sir. They get jostled, absorbed, re-emitted, bounced around like a frantic toddler in a ball pit made of nuclear soup. You might think the light of a star is fast, and outside the star, sure, it travels at light speed, but inside the core, the journey is laughably slow. A single photon can take thousands, even millions, of years to make it from the core to the surface. Some estimates say it could be up to 1,000,000 years. A photon born when woolly mammoths walked the earth might just now be escaping your sun. That's the fringe fact of the section. Stars shine with light that was not made this morning. You're basking in million-year-old sunlight, served piping hot by our star's slow, squishy transport system. Once the photon finally makes it to the outer layers of the star, it's free, released, unleashed. It soars outward at last through the photosphere, the star's visible surface, and into space. That's the glow you see when you look up. That's starlight, pure, ancient, and kind of stubborn. Fusion also creates neutrinos, ghostly little particles that barely interact with anything at all. While photons bounce around like nervous bees, Neutrinos leave the core in mere seconds and pass straight through planets, people, entire galaxies. There are trillions passing through you right now. You're basically a neutrino turnstile. They don't stop, don't care, and you'll never feel them. Rude, honestly. Meanwhile, the star you're watching hums with contentment. Fusion keeps it stable. The light keeps flowing, and planets might already be coalescing around it. The energy released is staggering. Our sun, for example, emits 3.8x 1026 watts. That's the same as detonating 91 billion megaton nuclear bombs every second. And yet we just call it a nice day when it shines. You can't help but admire how stars in their long, stable middle lives act as factories. Fusion not only creates helium, it begins crafting heavier elements too. In larger stars, this includes carbon, oxygen, neon, and eventually iron. Every atom of calcium in your bones, every molecule of iron in your blood, was born in a star that lived, burned, and died long before you ever Googled, "Why is the sky blue at night?" Stars aren't just points of light. They're ancient foundries, building blocks for life. Every atom heavier than hydrogen and helium. Stellar leftovers. You're literally made of starlight, slowed down into molecules and organized just enough to scroll tick-tock while eating cereal. Eventually, every star runs out of fuel. Even this new one you're watching will one day lose the balance between gravity and fusion. But that's a story for later. For now, it burns steadily, a little brighter every second, pushing back the dark. As you float just above the photosphere, you notice how the light feels different now. Less chaotic. The randomness of the core has given way to radiance, clarity. The journey from fusion to freedom is nearly complete. Soon, that light will travel outward across space, headed for any lucky set of retinas that happens to be looking up. Maybe, one day, it'll land on someone else's eyelid, just like the starlight you caught earlier. And that's how it begins again. You now find yourself tangled inside a labyrinth of light. Not gentle starlight brushing your cheek in the night, no. This is the place where photons are born and immediately stuck. You're deep inside the heart of a star, that glowing furnace you admired from the outside just moments ago. And here, the light doesn't shine, it struggles. Every photon here is a prisoner. It's a hard thing to grasp. After all, light is supposed to be the fastest thing in the universe, beaming across space, bouncing through glass, dazzling across your screen in real time. But not in here. Inside a star, light moves at the speed of molasses in a snowstorm. It's trying. Oh, it's really trying. But this place is dense. The core is packed tighter than your schedule during finals week. The photons born in the wild thermonuclear chaos of fusion don't get to soar. Instead, they ricochet through a dense crowd of charged particles. Every millimeter, they're absorbed and spat back out. Absorbed, spat out. Again and again, like toddlers trying to leave a birthday party but being redirected by 12 aunties offering more cake. You follow one particularly unlucky photon. Let's call it Phil. Phil the photon is brand new, bursting with energy from hydrogen fusion. He's full of purpose, ready to travel the galaxy. But first, he bumps into a proton, absorbed, then re-emitted in a totally new direction. Then again, and again, and again. Phil's journey is a random walk, like trying to escape a forest blindfolded by taking one step in a random direction every minute. Scientists call this a random walk or Brownian motion, which is science speak for hope you packed a lunch. And it takes time, a lot of time. For our own sun, photons like Phil take anywhere between 10,000 and 1,000,000 years to reach the surface. That's right. The sunlight that hits your face today might have been born when woolly rhinos were still fashionable. Historians still argue whether this lag, this slow crawl of light, was fully appreciated when we first figured out fusion. Early models didn't always include it, and for a while, people imagined photons zooming out of stars like giddy fireflies. But nope, they're more like overworked commuters, jostled for centuries before finally getting out the door. What's keeping them trapped? Plasma, pure electric glowing plasma. The core of a star is a soup of free protons and electrons, too hot for atoms to form properly. This charged soup is incredibly effective at interacting with photons, grabbing them, scattering them, throwing them like dodgeballs. The result? Even though photons travel at the speed of light, their progress is heartbreakingly slow. And here's your quirky tidbit for the night. There's a theoretical chance, small but fun, that the photons reaching your eyeball today are not the same ones created in the core of the sun. Some scientists argue that the energy from fusion gets absorbed and re-emitted so many times, the original photons essentially vanish. What you get is light descended from the originals, not the actual baby rays, like cosmic great-great-great-grandchildren. Either way, the journey is long. As you drift along with Phil, you start to notice how his energy changes. Each collision robs him just a little. By the time he reaches the upper layers of the star, the radiative zone, he's no longer the energetic gamma ray he once was. He's been softened, cooled, smoothed into visible light or maybe even infrared. This part of the star is quieter. The density drops. Photons can travel farther between collisions now, still zigzagging, yes, but less chaotically. It's like trying to run through a crowd at a festival versus walking through a nearly empty mall. You and Phil are making progress now, up and out. Next stop, the convective zone. Here things get bubbly. This layer is more like boiling soup than a light maze. Huge blobs of plasma heat up, rise, cool off, and sink again. This churning convection moves energy much faster than radiation. Think lava lamp but scaled up to planet-sized blobs, all rolling and folding over one another. Photons here hitch a ride on these convective currents, like carpoolers catching a lift. They're not being absorbed and re-emitted quite as much. Instead, they ride the thermals up to the photosphere, the visible surface of the star. That's where things get bright. That's where light escapes. And that's where Phil, if he's still with you, finally breaks free. You burst out alongside him into space. The difference is instant. No more collisions, no more chaos. Just a clean, silent trajectory through the vacuum. A straight line at last. From here, it's smooth sailing, unless you count the occasional rogue asteroid, dust particle, or someone's weather balloon. You look back at the star, now glowing in full from the outside again. It's impossible to see the photon prison from here. No sign of the zigzagging chaos inside, just radiance. Clean, consistent, eternal-seeming radiance. It's a good reminder that everything you see in space is filtered. The smooth surfaces, the gentle glows, the twinkling points, they hide violence, pressure, drama. Stars are full of secrets, and light is just their very patient courier. You ride now on a fresh photon, one that might reach a planet in another system, or a telescope drifting silently in orbit, or maybe, just maybe, your own waiting eye back on Earth. It's no longer the tortured light trapped in the core. It's free light now, beaming through the void. A message from the universe traveling at light speed, wrapped in silence. And you, lucky dreamer, got to follow it all the way out. The moment a photon breaks free from the star's surface, everything changes. No more pinball, no more obstacles. It races outward at 186,000 miles per second, clean as a whistle, pure as a dream. And you, floating in its wake, get to feel the silence of space rush around you, not like wind, but like the absence of absolutely everything. You followed this particular photon for a long time. From the chaos of fusion in the core, through the jostling interior layers, to the final leap through the photosphere, the visible surface of the star. That's where light officially escapes. It's not a hard surface, of course. Stars aren't rigid. They're like gelatin made of plasma. But from this altitude, it looks almost smooth. The photosphere shines like a sea of white-hot grains, each granule a bubbling convection cell, churning silently, miles wide. The photon you've chosen zips upward and away, carving its place into space. From here, the light no longer fights to be seen, it is seen. It floods the emptiness. No turning back now. Of course, light doesn't know where it's going. It doesn't aim. It just goes. If there happens to be a planet in its way, great. If not, it'll keep traveling for billions of years until it's absorbed by something, or not at all. That's the thing about photons. They're immortal as long as they don't hit anything. This one is headed toward Earth. It's a long, empty road. The vacuum of space isn't quite nothing, but it's close. A few atoms per cubic meter, a bit of dust, a sprinkle of cosmic rays, the occasional drifting chunk of interstellar debris. But otherwise, it's the ultimate minimalist highway. No exits, no roadside attractions, just infinite dark and the glow of distant stars in every direction. As you drift alongside the photon, you start to realize how perfect light is at making distance irrelevant. This photon, after all, takes just over 8 minutes to reach Earth from the Sun. That's it. From fusion reaction to retina in under 9 minutes once it escapes. It could have spent 10,000 years trapped inside the Sun, but once it's out, it's a speed demon. You pass Mercury, glowing like a scorched pebble. You skirt Venus, whose thick atmosphere reflects back much of the light, greedy, shimmering. And finally, you see Earth. Blue, quiet, floating like a marble dipped in sunlight. Light slams into the top of the atmosphere and some of it is scattered. That's why the sky is blue during the day. Shorter wavelengths like blue and violet scatter more easily. But most of the violet is absorbed, and your human eyes are biased toward the blue range anyway. So blue wins. Your photon continues downward, straight through the atmosphere, dodging dust, water vapor, even a stray insect wing. Finally, it hits something. A tree leaf, a window pane, the side of someone's cat. Or if it's lucky, it slides right into the pupil of a curious earthling, lying in bed, eyes open, wondering about stars. And just like that, the journey ends. You blink, the photon is absorbed, its energy turned into a neural signal. Your brain says, light or sunlight. Or maybe you don't even notice. Just warmth on skin, brightness through eyelids, a mood shift, subtle and primal. Historians still argue whether ancient skywatchers understood that light moved. The idea that it traveled at a specific speed didn't land until centuries later. Empedocles suggested it in ancient Greece, but it took until the 1600s for anyone to measure it properly. That happened thanks to a Danish astronomer, Ole Romer, who realized that light didn't instantly reach Earth from Jupiter's moons. There was a delay, a measurable one. Light, it turns out, takes time. Even now, we use that delay to measure distance. A light year is exactly what it sounds like. The distance light travels in a year, about 6 trillion miles, give or take. So when a star is 10 light years away, you're seeing it as it was 10 years ago. You're seeing its past. That's the real kicker with escaping starlight. It's not just illumination, it's time travel. When you look at the stars, you're seeing old news. Light, arriving from billions of miles away, tells you about events that may no longer be happening. That star you see, it could be gone, blown up, collapsed, cooled. But its light is still en route and will keep arriving for centuries or millennia, like a postcard from a traveler who's long since disappeared. Here's your quirky gem. Some of the starlight reaching Earth now has been gravitationally lensed, bent and warped by massive objects in between, like galaxies and black holes. The light curves around them like water flowing past a rock, creating weird duplicates, distorted smears, or even ring-shaped illusions in our telescopes. Nature's funhouse mirror. You coast alongside a few more photons, all with their own trajectories, their own tiny destinies. Some are headed for telescope lenses on mountain tops. Some will hit solar panels and get turned into electricity. Some will crash into concrete and vanish. And a few, a precious few, will catch the attention of human eyes who will wonder, what am I really looking at? You watch one more. It travels from a far-off star, a red dwarf halfway across the galaxy. It took years, decades to arrive. But tonight, finally, it strikes the lens of a backyard telescope. A kid peeks through the eyepiece and gasps, just a point of light. But to her, magic. That's the real gift of starlight. Not just beauty, not just warmth, but information. Every escaping photon is a message in a bottle whispering something about the universe. I came from here. This is what I saw. This is how I burned. And as long as someone is looking, someone is curious, someone is willing to wonder, those messages don't go unheard. They become part of you. You're floating again, starlight at your back, the void stretching endlessly in front of you. But this time, you're not clinging to one single photon. You're riding shotgun with millions. A whole wavefront of light, like a ripple on an invisible ocean, spreading out from its stellar source. It's a gentle reminder. When light escapes into space, it doesn't travel alone. It spills out in every direction, a sphere of brilliance expanding at light speed. You're tracing the outer edge of that sphere now, watching the leading edge of an ancient message glide past planets, moons, and empty interstellar corridors. A message not made of words but of wavelengths. This is how starlight travels across time. And it doesn't need roads. You turn your attention to a nearby star, one you've seen before but never quite appreciated. Deneb, part of the Summer Triangle. Its light has been traveling for more than 2,600 years to reach Earth. That's before Rome was a big deal, before the Parthenon, before vowels in the English language were really even sorted out. And yet tonight, that light finally lands on your world, soft, precise, unapologetically late. That's the thing about space. It doesn't rush. Time moves differently when you stretch your sense of scale. 100 years, that's nothing to a photon, a million, a decent commute. Some stars lie so far away that their light has been traveling since long before Earth was Earth, since it was just dust, tumbling quietly around a younger sun. The farthest individual star ever detected is called Earendel, named after a Tolkien character, because of course it is. Its light began its journey over 12.9 billion years ago. That's nearly the entire age of the universe. The kicker: we only saw it recently because its light got magnified by gravitational lensing. If that photon had been nudged even a degree to the left, it would have missed us by 1,000,000 light years. Historians still argue whether ancient astronomers guessed the scale of cosmic distances. Some figured stars were just beyond the moon. Others imagined them as far-flung candles stuck to the edge of the sky. The idea that stars are sun-like objects, separated by trillions of miles, took centuries to gain traction, and even longer to be proven. Now you know better. Now you feel it. You and the photons continue your journey together, coasting through the black. Sometimes you cross regions of space where starlight grows thin. Cold, quiet patches where distant galaxies are just faint smudges. And in these spaces, time seems to stretch. There's no ticking, no heartbeat, no sunrises or sunsets. Just movement, silent, relentless. Then, like a whisper in the dark, a new star's light catches your attention. But it's not fresh. It's ancient. It left its host billions of years ago from a star that's long dead. The light has been traveling ever since, unaware that its source has gone supernova, collapsed, or simply cooled into obscurity. This is the cosmic equivalent of receiving a voicemail from someone who's already moved away, or passed on, or never existed the way you thought. And yet the message arrives, perfect, intact, as if it were new. There's something oddly comforting about that. Light doesn't care what's happened in the meantime. It doesn't care about news updates or galactic gossip. It just delivers its data, wavelengths, intensity, frequency, like a loyal postman operating across eons. Here's your quirky footnote. Starlight can be redshifted by the expansion of the universe. That means as it travels, the space it moves through stretches, pulling the light into longer, redder wavelengths. It's not just getting tired, it's getting cosmologically dragged. Think of it as the universe gently pulling the brakes on a very old delivery van. The farther a galaxy is, the redder its light becomes. That's how we know the universe is expanding. Every beam of ancient starlight that arrives stretched and softened is basically shouting, "I've come a long way and space is getting bigger." You ride one of these redshifted beams for a while, watching the background stars fade from blue-white to orange to deep infrared red. You've crossed into light invisible to human eyes now, but still very much real. Our telescopes pick it up. Our instruments interpret it. Our minds imagine what it must have looked like when it first blazed to life. Occasionally, you see a star explode. No, really. A supernova from millions of years ago. Its light still on the way, still catching up. The burst of energy radiates outward in all directions, bright enough to outshine its entire galaxy for weeks. And when that light reaches Earth, it'll trigger observatories, shake up astronomers, and maybe even catch a curious pair of eyes peering through binoculars from a dark backyard. You're seeing the event now in its rawest form. Waves of radiation flaring outward, packed with X-rays, gamma rays, visible light, neutrinos. It's a luminous obituary, the final word of a massive star. And then silence again. A return to the hum of old photons making their way through space like seasoned travelers. They don't rush. They don't get lost. They just go. You finally return to your own star, your sun, and notice how young it looks now. Its light only travels 8 minutes to reach Earth. 8 minutes. A blink. A hiccup. Practically a text message in cosmic terms. And yet that light powers every green leaf, every weather system, every sunbeam bouncing off pavement or skin. Your entire day depends on 8-minute-old light. It makes you wonder how fragile, and yet how resilient, light really is. It can be scattered by a molecule, but it can also cross 13 billion years and arrive intact. It can warm your face or blind a sensor. It can pass through glass but not your hand. It can tell you the temperature, speed, motion, and chemical makeup of a star it never even knew it left. This is how starlight travels. Not just through space, but across time, through silence, through dust, through wars, births, extinctions, awakenings. It arrives anyway. Tonight, maybe some of it will land on you. And you won't even notice, except for the quiet feeling that the universe somehow is watching back. You're drifting now into the fire, the part of the journey where starlight stops being abstract and starts showing its true colors. Literally, the color of a star isn't just a pretty detail. It's physics. It's heat. It's the raw, glowing math of temperature translated into light. You hover near a blue giant first. It's impossibly bright, like 1,000 suns fused together and set to maximum. Its glow isn't just intense, it's fierce, sharp. It hums in a higher key with waves of light leaning toward the ultraviolet. If starlight had teeth, this one would have fangs. And here's the thing. That blue isn't just for show, it's a thermometer. You see, stars don't burn in flames. They shine from heat, blackbody radiation if we're being technical. The hotter a star is, the bluer its light. The cooler it is, the redder. It's the same principle that makes metal glow red when it's heated, then orange, then white hot. Light is just a symptom of temperature, a color-coded fever chart of stellar mood swings. So that blue star, it's burning at upwards of 30,000 Kelvin. Meanwhile, our cozy sun, which looks yellow to most of us, is actually closer to white when viewed from space, about 5,800 Kelvin. It only looks yellow from Earth because our atmosphere scatters some of the blue away. Classic Earth move, altering the vibes. You float now toward a red dwarf. It's dimmer, calmer, radiating in longer, slower waves. If the blue giant is a firework, this star is a candle, gentle and enduring. These cool stars hover around 2,500 to 3,000 Kelvin, glowing with a soft, rust-colored light that barely outshines the void around them. And yet, they're the most common stars in the universe. Billions of them, quietly simmering in the background, waiting for someone to notice. Historians still argue whether early scientists understood why stars had different colors. They noticed, of course, cataloged them even. But it wasn't until the 19th century that the connection between temperature and light became clear. Before that, many thought color was a result of distance or even dust. To be fair, cosmic dust does redden light. It's called interstellar extinction. But the color of a star itself, that's baked in at the source. You stop now between a few stars in a rich cluster. Some burn blue-white, some orange, a few barely visible in a faint red haze. It's a stellar rainbow, and it has a name, the Hertzsprung-Russell diagram. Okay, it's a chart, not a party. But it's one of the most important tools in astronomy, a scatter plot that shows the relationship between a star's brightness and its temperature. It tells you where a star is in its life, what it's burning and what it's becoming. Hot and bright. That's a young, massive star burning through fuel fast, basically the rock star of the stellar world. Cool and dim. That's a red dwarf packing itself for a trillion-year lifespan, a star like the sun. Somewhere in the middle, stable, well-adjusted, and middle-aged. It has preferences. It wears SPF. It listens to podcasts. And here's your fringe fact for the evening. Stars can sometimes change color, not just over billions of years, but during short, dramatic phases. Take a dying red supergiant. It may appear reddish now, but just before it goes supernova, it'll heat up, turn yellow-white, and then maybe blue again, like one last costume change before the curtain drops. Back near Earth, our own sun gives us a front-row seat to the color-temperature show. Its surface glows in all visible wavelengths, but the peak emission falls in the green-yellow range. Again, thanks to atmospheric scattering and how our eyes are tuned, we perceive it as yellowish-white. But space telescopes confirm it. The sun is a near-perfect blackbody radiator. Not too hot, not too cold, just right. Goldilocks would approve. You glide now into a beam of starlight and let it wash over you. It's not just one color, it's a spectrum. Even the simplest starlight is a symphony of frequencies, layered and balanced. The visible color is just the part your eyes catch. Most stars also emit in infrared, ultraviolet, even X-rays. Each wavelength carries information. Each has its own vibe. Remember those blue giants? They pump out ultraviolet like it's going out of style. Invisible to your eyes but deadly in high doses. Hang out near one of those for too long and your molecules start filing exit paperwork. Red dwarfs, on the other hand, lean heavily on the infrared. Great for warm toes, not so great for tanning. Now imagine you're holding a prism, or a CD, or anything else that bends light into its components. You pass a beam of starlight through it and out spills the rainbow. Violet, blue, green, yellow, orange, red. The color wheel of the cosmos. You're not just looking at pretty colors, you're reading temperatures, compositions, and ages. Every color tells a secret. Want to know something even weirder? Our human eyes evolved to be most sensitive to the exact range of colors our sun emits most strongly. We are literally built to see solar starlight. If we had evolved under a red dwarf, our vision might peak in infrared. Under a blue star, maybe we'd be UV detecting like cosmic bees. But here we are, walking spectrometers tuned to the star we orbit. Starlight isn't just out there. It's in here, on our skin, in our bones, in our tools and our eyes, and its color is the quiet way it speaks. So the next time you see a blue star twinkling over the horizon or a faint red ember near the edge of the sky, remember, you're looking at temperature, at time, at distance, at chemistry and fate encoded in color. It's not just light. It's an ancient heat signature, whispering across the void. And somehow, you've learned how to listen. You're cradling starlight now, not just basking in it, but unraveling it. Like a magician pulling a scarf from a sleeve, you coax each hidden color from a single beam, stretching it into a band of pure information. You've stepped into the world of spectroscopy, where light is no longer just illumination, it's language. You start with something simple, a prism, just glass bent at the right angles. You guide a single beam of starlight through it and it splinters instantly into a rainbow. But this isn't just your garden variety rainbow, it's a spectrum. A pure record of wavelengths, a barcode for the universe. Red bleeds into orange, then yellow, then green and blue and violet. But something interrupts the flow. Tiny dark lines, like scratches on film, appear across the colors. You lean closer. What you're seeing is nothing short of sorcery. These are absorption lines, gaps in the rainbow where specific wavelengths have been removed. Removed by what exactly? Atoms. As light escapes a star's surface, it passes through the outer layers of gas in the star's atmosphere. Atoms in that gas absorb very specific wavelengths of light, just the ones they like, thank you, and those wavelengths disappear from the spectrum. Each element has a unique set of preferences, a kind of light-based Tinder profile. Hydrogen, for instance, absorbs red and blue-violet in distinct places. Helium's got its own vibe. So does sodium, calcium, iron, and the rest of the periodic table. And there's your first big revelation of the night. Stars speak in spectra. Historians still argue whether Joseph Fraunhofer, who first mapped hundreds of these spectral lines in sunlight back in the early 1800s, fully understood what he'd stumbled onto. He didn't know why the lines existed, just that they were there, consistently, like cosmic fingerprints. Only later would scientists decode the mystery. Atoms absorbing starlight in ways so precise, you could read a star's chemistry from across the void. It's wild. You don't need to visit a star to know what it's made of. Just stretch out its light. Read the barcode. The dark lines tell you what elements are present in what amounts, even at what temperature and pressure. It's like eavesdropping on a conversation you can't hear, but can definitely translate. Want your fringe fact for this section? Here you go. The element helium was discovered in the sun before it was ever found on Earth. In 1868, scientists observing a solar eclipse noticed a bright yellow spectral line that didn't match any known element. They named it helium, after the Greek word helios, sun. It wasn't until decades later that helium turned up in terrestrial rocks. So yes, you could say we found it up there before we found it down here. Now back to your rainbow. You shift your prism and the starlight dances again. This time you're looking at a hot, young star. Its spectrum is rich in hydrogen, sparse in metals. Metals, by the way, is astronomer shorthand for any element heavier than helium, which is most of them. Stars formed early in the universe are metal-poor. Newer ones, like our sun, are metal-rich. That's how you can tell the galactic newcomers from the ancient ones, by how many times the universe has recycled their atoms. Spectra don't just reveal ingredients, they reveal motion. If a star is moving toward you, its spectral lines shift slightly toward the blue end of the spectrum, a phenomenon called blue shift. If it's moving away, the lines slide redward, redshift. These tiny changes in wavelength are like speedometer readings. They let you measure stellar drift, orbital velocity, even the expansion of entire galaxies. You hover now near a binary star system, two stars orbiting each other in an endless celestial waltz. Their spectra shift back and forth like a duet, redshift, blue shift, redshift, blue shift, as they move toward and away from you. You're not just watching them dance. You're listening to their rhythm in light. From this alone, astronomers can calculate their masses, distances, and the eccentricity of their orbit, all without ever leaving Earth. That's the real magic of spectroscopy. It's the ultimate long-distance relationship tool. You float back toward our sun's spectrum, more familiar now. You notice the hydrogen lines, called the Balmer series, running like rungs on a ladder through the visible range. You catch the calcium, H and K lines in the violet end. Even the narrow signature of sodium, which you might also recognize from street lamps. And you realize something quietly stunning. The same laws that govern starlight also govern light on Earth. The same atomic interactions that paint the sun's spectrum shape the glow of neon signs, firework bursts, and the warmth of an incandescent bulb. It's all the same physics, scaled across the cosmos. You feel it now, not just the light, but the meaning. The way each beam carries a history, a chemical biography, a physical timestamp, even emotions if you're feeling poetic. When you peer through a spectroscope, you're reading starlight like a letter from a pen pal who's 200 light years away, writing in a dialect of electromagnetic pulses and atomic whispering. And the letter always begins the same way. Dear curious creature, here's everything I know about where I came from. And you learn to write back, not with light but with questions. Questions that stretch across years, across light years, across centuries of sleepless thinkers who stared into prisms and rainbows and wondered, what else can I learn from the colors? So tonight, lie back and let the spectrum stretch. Let the light unravel slowly, like threads from a tapestry woven in a star's heart. Because hidden in every hue, in every dark absorption line, in every whisper of color, is a truth so intimate it might as well be a lullaby. Now that you've learned how to stretch a single beam of starlight into a barcode of colors and secrets, you're ready to read its full autobiography. Because tucked inside those spectral lines, the dark interruptions, the subtle shifts, the faint glows barely clinging to visibility, are the ingredients of the universe itself. And tonight, you're going to find out exactly what stars are made of. You drift again beside the sun, not to bask in its warmth, but to look through it. Not with your eyes, but with the quiet confidence of someone holding a spectroscope and a healthy amount of cosmic curiosity. Its glow is rich and layered, a feast of frequencies, and you begin to peel it back. Hydrogen first and foremost. It dominates the scene. Not surprising, really. Hydrogen makes up over 90% of a typical star's atoms. It's the OG element born in the first few minutes after the Big Bang, when the universe was a very hot, very cranky infant. You see its spectral signature clearly. The Balmer lines, etched in deep violet and red, strong and unmissable. Next up, helium. Less obvious but just as essential. It makes up most of the remaining 9%. Helium is the result of fusion, the byproduct of hydrogen smashing together under pressure. It's a noble gas which sounds fancy and aloof, but in a star it's just very, very chill. Helium doesn't do much except sit there and remind you that fusion happened. Then things get interesting. Sprinkled among the hydrogen and helium are trace amounts of other elements: oxygen, carbon, nitrogen, calcium, iron, neon. Tiny percentages. Dustings, really. But these tiny details change everything. Carbon tells you that the star has been around long enough to start producing heavier elements in its core. Oxygen hints at the life cycle of previous generations of stars, which exploded and recycled their guts into the raw material for the current one. Calcium gives away details about the star's surface temperature and pressure. And iron. Iron is a red flag, a warning that the star is nearing its end, because iron doesn't fuse into anything heavier without costing energy. Once a star starts building up iron in its core, the countdown begins. Here's your quirky nugget for tonight. Stars never truly make iron until they're about to die. In fact, iron is kind of the boss level of stellar fusion. A star can fuse elements up to iron and still release energy. But trying to fuse iron into something heavier costs more energy than it gives off. So when the core is full of iron, the engine stalls. Gravity takes over. Collapse begins. And then, boom. But that's a death story. We're still in the full bloom of life here. You glide away from the sun toward other stars, each with their own unique chemical ID tags. Some stars are richer in elements heavier than helium. Astronomers call these metal-rich, even though that includes things like carbon and oxygen. The more of these heavier elements a star has, the more likely it is to host rocky planets like Earth. Stars born early in the universe are metal-poor. They didn't have much to work with, just the leftovers of hydrogen and helium. But stars like our sun, second or third generation, born from recycled stardust, upcycled matter. Historians still argue whether the concept of stellar recycling was understood when we first discovered that stars produce elements. For a long time, scientists assumed stars were static, unchanging. But then we found the fingerprints of older stars inside newer ones. We saw carbon in places where it shouldn't be. We noticed iron in baby stars and realized they'd inherited the ashes of ancient giants. Which means this: the calcium in your bones, the iron in your blood, the oxygen in your lungs, it was all made in a star, not metaphorically, not poetically, literally. You are stardust that woke up and started wondering about itself. And if you want to know what kind of star donated the atoms you carry around each day, all you need is a spectrum, a stretched-out barcode of light studied carefully. That's the cosmic recipe. That's the ingredient list. You float now near a carbon star, a rare breed with more carbon than oxygen in its atmosphere. The light here is tinted red, soft and moody, like velvet drapes in an old library. Its spectrum is riddled with molecular bands, carbon compounds, including cyanogen and carbon monoxide. Not the coziest neighbors, but fascinating guests at the atomic dinner party. And then you move on to a metal-poor star, older, colder, wiser. It emits light with fewer absorption lines, fewer elements, a cleaner spectrum. It's like listening to a song with fewer instruments, simpler maybe, but no less moving. Finally, you return to Earth's orbit, peeking at starlight as it's captured by modern telescopes. You imagine teams of scientists decoding spectra on monitors, cross-referencing databases of elemental lines, trying to figure out if that star they're watching might be like ours, or wildly different. Some are looking for planets, others for habitable zones. A few are chasing stellar oddities, stars with too much lithium or too little iron or strange ratios of rare isotopes. Every deviation is a clue. Every star is a data point in the giant cosmic game of how did we get here? And now here's the quiet twist: Earth's atmosphere. It has its own spectral signature, too. When starlight passes through it, some extra absorption lines appear, caused by molecules like oxygen, water vapor, and carbon dioxide. These telltale lines are so familiar, astronomers call them telluric lines. They're a nuisance to some, a guide to others. But here's the real trick. When we study exoplanets, worlds orbiting distant stars, we look for similar telltale lines in the light reflected by those planets. If we find oxygen or water or methane in the light coming off another world, we might be looking at life. So you're not just reading stars when you stretch their light. You're also eavesdropping on their planets, their atmospheres, maybe even their ecosystems. It all comes back to the spectrum, a quiet rainbow of truth, held in place by the laws of physics. And read patiently by the only creatures in the universe known to wonder what stars are made of, while wrapped in the light of one. You're lying still now, eyes soft, brain quietly buzzing from the realization that every star has a story, told not in words or whispers, but in light stretched across time. But tonight, you're about to read those stories in reverse. You're about to look not just up but back, because starlight isn't just illumination, it's a time machine. You blink and you're gazing through a telescope, not a backyard one this time, but a behemoth, perched high above the clouds or floating quietly in space, far from Earth's noisy breath. The lens is wide, the mirror polished to perfection, and what you're looking at isn't just far away, it's ancient. The light entering your eye, or rather your mind, has been on a journey for millions, sometimes billions of years. Every photon is a timestamp, a relic, a traveler who left home long before humans ever named the stars. Here's the simple, glorious truth. When you look at something in space, you are not seeing it as it is. You're seeing it as it was, always. Your own sun. You see it with an 8-minute delay. If it vanished right now, you'd have no clue until your next stretch break. Alpha Centauri. You're seeing it as it was 4 years ago. Sirius, 9 years ago. The Andromeda Galaxy, more than 2.5 million years ago. That means the fuzzy blob you see through binoculars is how it looked when early humans were just starting to figure out how pointy sticks work. Historians still argue whether the first astronomers truly grasped this concept, that starlight is old light. Ancient philosophers thought stars were fixed, eternal. Some believed they lived forever. Others assumed they renewed themselves each night. But none could have guessed that the stars were giving us a live broadcast from the past. Now you glide past telescopes, radio, infrared, X-ray, gamma. Each is tuned to a different wavelength of starlight, and each sees the universe in a different time window. The James Webb Space Telescope, for instance, sees in the infrared. That means it's perfectly designed to spot ancient, distant galaxies whose light has been stretched by the expanding universe into longer, redder waves. You drift into one of those waves. It's not visible to the naked eye, but it's still light, just slower, gentler, aged by time. You follow it back farther and farther until galaxies begin to blur and vanish, and all that's left is a dim, reddish glow. This is the cosmic microwave background, the oldest light in the universe, still echoing from the Big Bang itself. It's 13.8 billion years old, the literal afterglow of creation. And guess what? We can still detect it. With radio telescopes, satellites, and really good math, we map this faint light like archaeologists brushing dust off bones. Every tiny fluctuation, every uneven smudge in the background tells us how galaxies formed, how matter clumped, how stars were born. You see it now. The universe isn't just a place. It's a timeline, a layered scrapbook of light. The farther you look, the older the light gets. There is no present, really, only a continuous peel back into the past, unfolding one photon at a time. Your fringe fact of the night. The Hubble Space Telescope once stared at an empty patch of sky for 10 straight days. Everyone expected nothing, just blackness. But when the image came back, it was full, absolutely full of galaxies. Over 10,000 of them packed into what looked like a blank square. That became the Hubble Deep Field image. A snapshot of the early universe captured by patiently collecting ancient light, one photon at a time. You lean closer. Those tiny galaxies in the deep field, many of them don't exist anymore. They've merged, aged, evolved. Some have collapsed into black holes. Others were torn apart by gravitational tides, but their light remains, a record, a cosmic ghost. And now you feel it, that beautiful ache in your chest. The ache that comes from realizing you are surrounded by light that left before your ancestors had names. Light from stars that died before Earth cooled. Light that traveled across time just to land softly in the lens of a telescope or in your half-lidded gaze. And the weirdest part, you do the same. You give off light too, not just infrared warmth from your skin, but reflected photons bouncing from you into the night. Some of those stray upward, out through the atmosphere. Most will hit dust, water, ozone, but a few, a very few, they'll escape. And they'll travel through space, across time. They'll take a snapshot of you as you are tonight, right now, and carry it into the future across stars, past sleeping planets, through nebulae and emptiness. Maybe no one will ever catch them, but they'll be out there. A record of you baked into the universe's long, slow breath. So the next time you look at a star and think, I wonder what it's like right now, remember. What you're really seeing is a memory, and what it's seeing, if it's still there at all, is yours. Because starlight is always late, and always somehow right on time. You lie still now, letting your mind quiet as the stars above you begin to shift, not in space but in meaning. Some of the points of light you see tonight don't shine because they're still alive. They shine because they were. What reaches you is ghost light, radiance from stars that have long since winked out, exploded, or collapsed into silence. Starlight doesn't care if the star that made it is gone. It just keeps going. You float beside one of these phantoms now. A white dwarf, a stellar corpse glowing faintly with the heat of what used to be. It no longer fuses elements in its core. It doesn't burn. It just radiates stored heat, slowly cooling like the embers of a fire that once roared. And yet, even in death, it sends out light. Light that might travel for eons, still arriving at unsuspecting eyes who think it's a star like any other. But it's not. It's a tombstone made of plasma. This white dwarf was once a star like our sun. It spent billions of years fusing hydrogen into helium, quietly bathing nearby planets in light. Then it swelled, dramatically, rudely into a red giant, consuming anything that drifted too close. And when it could fuse no more, it shed its outer layers into a planetary nebula and left behind this tiny, hot core, dense, bright, and quietly dying. Historians still argue whether the ancient skywatchers ever suspected some of the stars they saw were alive. Many cultures saw stars as eternal beings, gods, ancestors, permanent fixtures. The idea that a star could die, that it could explode, vanish, or shrink into darkness, that took science and a bit of imagination. You drift now toward one that didn't go gently. This one went supernova. You don't see the star itself anymore, it's gone. What you see is the remnant, a sprawling nebula of twisted gas and elemental ash. One moment the star was fusing its way toward iron. The next, its core collapsed, triggering a cataclysm so bright it could outshine an entire galaxy. For weeks, this single point of light blazed in the sky, and then darkness. But the light it emitted during its final breath, still traveling, still arriving. You coast along that light now, still visible in far corners of the cosmos, brushing past alien moons, pinging off frozen comets, slowly heading toward nowhere in particular. That's the thing about supernovae. They're brief, but their light lasts. Here's your fringe fact. In 1054 CE, Chinese astronomers documented a guest star in the daytime sky, bright enough to cast shadows. It remained visible for weeks. That explosion was the birth of the Crab Nebula, which you can still see in telescopes today. It's a supernova remnant with a rapidly spinning neutron star called a pulsar at its heart. That was nearly 1,000 years ago, but the light from that event, it had been traveling for more than 6,000 years before it reached Earth. In other words, when those astronomers looked up, they were watching the delayed fireworks of something that died long before the pyramids were even old. You drift near the Crab Nebula now. Its threads of gas are colored by glowing elements, oxygen, sulfur, hydrogen, each emitting its own eerie hue. You watch the pulsar in the center, blinking in rapid rotation like a cosmic metronome keeping time. It's the leftover core of the star, collapsed into something so dense it defies comprehension. A single teaspoon of neutron star would weigh as much as a mountain. So, don't spill that on your carpet. Not all stars explode, some just fade. You visit a red giant next, massive, bloated, unstable. It pulses softly like a heart with arrhythmia, its outer layers already loosening, preparing to drift away. One day it will become a white dwarf. Its light will continue, but its structure, its starness, will dissolve. And then there are stars that vanish completely. You know where you're going next, don't you? The black hole. You hover just outside the event horizon of what was once a massive star. It died in spectacular fashion and then collapsed inward, so tightly, so completely, that not even light could escape. You see no glow here, just the warping of space around the edges. The light from nearby stars bends and twists, sucked into curves and spirals, like it's being swirled down a cosmic drain. But wait, there's a surprise. As matter falls toward the black hole, it heats up, forming an accretion disk that glows with terrifying brightness. The infalling material releases X-rays and gamma rays, screaming as it's stretched and torn. Some of that light does escape before crossing the boundary of no return. So even black holes in their own way can shine. You don't see the original star anymore, but its light, emitted in the moments before collapse, it's still out there somewhere, perhaps nearing another planet, or brushing your earthbound telescope as you lie still in the night. And here's the soft truth. Many of the stars you see in the sky could already be gone. Not in a scary way, just in a very slow, very vast one. Their light is still en route. Their death hasn't caught up to us yet. So you lie there, bathed in the light of celestial ghosts, receiving messages from across time, some joyful, some tragic, all indifferent. And somehow that makes it feel less lonely, not more. Because the stars that shine now, the ones long dead, the ones yet to be born, they're all connected in this vast, slow ballet. And you're watching the performance from the edge of the stage, wrapped in a blanket, surrounded by the ghosts of light. Maybe that's why we find comfort in the stars. Not because they're eternal, but because their endings still shine. You've been drifting through a fairly calm stretch of starlight. Ghost stars, white dwarfs, the silent unraveling of ancient light across time. But now you're headed toward the drama section of the universe, the ones that flicker, explode, drain, flare, and blink like they're trying to get your attention. These are the variable stars, and oh yes, the cosmic vampires. First up, the variable stars. These are the divas of the cosmos. They don't just shine, they perform. Their brightness fluctuates over time, sometimes in predictable patterns, sometimes like they're improvising a jazz solo. You drift beside one now. Its light pulses rhythmically, swelling and shrinking like it's breathing. This one is a Cepheid variable, and it's not just pretty, it's useful. The star's brightness varies with a precise period, like clockwork. And here's the magic. The period of its pulsing is directly related to its true brightness. So by measuring how long it takes to brighten and dim, astronomers can calculate how far away it is, just like that. That's a big deal. Historians still argue whether Henrietta Leavitt, who discovered this relationship in 1908, got the recognition she deserved. Spoiler, she didn't. But thanks to her work, Cepheid variables became the measuring sticks of the universe. Without them, we wouldn't know how far away most galaxies are. No Big Bang model, no expanding universe. Just a lot of confused astronomers squinting at the sky. You drift now to another kind of variable, a Mira star. This one changes brightness slowly over months. It's older, redder, and leaking matter into space in dramatic bursts. You watch as it exhales a shimmering shell of dust and gas, like glitter off a spinning disco ball. Mira variables are dying giants, flinging their outer layers into space as they wind down. And then, just when you're getting used to the rhythm, a sudden flare, a spike, a scream. This is not a gentle pulsing star. This one is chaotic, twitchy, violent, a flare star. Flares happen when magnetic fields on a star's surface suddenly snap and reconnect, releasing bursts of energy. It's like a solar tantrum. Your own sun does this too, occasionally launching solar flares and coronal mass ejections. But flare stars take it to another level. Some increase their brightness by dozens or even hundreds of times, all in a matter of minutes. You imagine being on a planet orbiting one of these stars. You settle into your morning coffee, and suddenly the sky turns ultraviolet. Not ideal. Hope you brought SPF 10 million. But we're not done yet. You turn toward the real drama queens, binary stars with problems. Here you find a pair of stars locked in orbit. But this isn't a sweet, slow dance. This is more like a crime scene. One star is larger, bloated, unstable. The other, a dense, hungry companion, a white dwarf, neutron star, or maybe even a black hole. You watch in quiet horror as the bigger star swells too close, and its outer layers begin to spiral toward its companion. The dense star feeds, literally siphoning material from its bloated partner like a vampire at a plasma donation clinic. Astronomers call these cataclysmic variables because, well, you can guess why. The material spirals in, forming an accretion disk, heating up from friction until it glows bright enough to be seen across light years. Sometimes the feeding triggers a massive explosion, a nova, where the infalling gas ignites in a flash of light. Sometimes it doesn't stop there. Sometimes the mass builds up until boom, a supernova. Fringe fact: some binary systems are so tightly wound that they orbit each other in mere hours. The stars are almost touching. One blink too long and you miss an eclipse. These are eclipsing binaries, and their combined light dips and rises like a heartbeat as they take turns blocking each other from view. We don't just see these dips, we track them. We learn their masses, their distances, their fates. You hover now above a double white dwarf system. They're dancing impossibly close, losing energy with every orbit. Slowly, they're spiraling inward. One day they'll merge. The result, possibly another nova, possibly a single, more massive white dwarf, possibly a supernova that tears them both apart. It's funny in a dark sort of way. Stars can live solo, stable, and boring lives for billions of years. But put too close together, and suddenly it's chaos, jealousy, drama, consumption, and sometimes literal obliteration. Maybe the universe just loves a messy romance. You turn now to a different kind of variability, one caused not by the stars themselves, but by us, or rather, by what's between us and them. Sometimes a star appears to dim and brighten not because it's changing, but because something is blocking its light. A planet, a dust cloud, even another star crossing in front of it. This method, transit photometry, is how we detect many exoplanets. A tiny dip in starlight, repeating like clockwork, tells us a planet is orbiting that star. So even the light missing from a star's glow can tell us something extraordinary. You lie back, letting the flickers and flares wash over you now, not as chaos but as rhythm. You realize the night sky isn't steady. It's alive, breathing, blinking, glowing, gasping. Some stars throb like hearts. Some vanish in moments. Others rise, blaze, and burn out before their light ever reaches us. And yet, all of it adds up to the same thing. A language. Not a quiet one, not polite, but full of emotion, motion, and long-distance shouting. You feel like you understand them now, not just the stars that shine steadily, but the ones that change, the ones that burst, bleed, grow, and give. The ones that can't help but be noticed, even across 10 billion miles of dark. You're drifting now toward the curve. Not a thing exactly, not a place or a star or a nebula. A curve, a bending of the fabric around you. Because as you've followed starlight across time through birth and death and explosive drama, you've probably wondered, does it ever get lost? Well, it doesn't, but it does get bent. This part of the universe, it's under the influence of something massive, not visibly massive either, something dark, something dense, something you wouldn't notice until it's already warped the path beneath you. You're entering the territory of gravitational lensing. Imagine this. Starlight, speeding in a straight line, suddenly encounters the warped gravity well of a galaxy or a black hole. It doesn't stop, it doesn't crash, but the space it travels through, that space is curved, and light, ever the rule follower, always moves in straight lines. So if the space itself is curved, light bends with it. You watch this in real time. A bright star behind a galaxy cluster should be hidden, and yet there it is, doubled, tripled, distorted into a smudgy arc. The light from that distant star has been warped around the massive object in front of it, magnified, redirected, and stitched back together in your view. It's not magic, it's Einstein. Literally, Einstein predicted this in his general theory of relativity. Light follows the geometry of spacetime, and mass, especially concentrated mass, changes that geometry. The result is a cosmic lens. You're not just seeing light, you're seeing light refracted by gravity. Historians still argue whether the 1919 solar eclipse that proved Einstein's theory was solid science or just a very lucky photographic experiment. But it worked. Astronomers measured the apparent shift in star positions as their light curved around the eclipsed sun. That tiny arc, it changed everything. Now you're floating at the edge of something much stronger than a galaxy. A black hole, not just massive but compact. Mass so concentrated, spacetime folds into itself. You're close enough now to see what light does here. It doesn't fall in, not if it's aimed just right. Some photons skim the edge of the black hole's event horizon, their path bending into a full circle. These are the famous photon spheres, where light literally orbits the black hole. That's right. There's a radius where photons can circle a black hole forever, caught in gravitational limbo. You float through one now, an endless carousel of light that can't quite escape but hasn't yet been devoured. Others take a slightly wider arc, bent just enough to graze the black hole and shoot back out toward the cosmos. These are the lensed photons, their paths distorted, their timelines stretched. You follow one that was emitted by a star behind the black hole. It curves gently, then violently, until it reaches your eyes as if the star were in the wrong place entirely. It's the ultimate cosmic illusion, and astronomers use it. Gravitational lensing doesn't just give us pretty light shows. It lets us see things we shouldn't be able to see. Distant galaxies hidden behind closer ones. Stars magnified by lensing events. Even individual exoplanets orbiting otherwise invisible stars, discovered because their gravity briefly bent the light of a background object. Your fringe fact: in rare cases, light can be bent into a complete circle around a lensing object. This creates what's called an Einstein ring, a full halo of light surrounding the lensing mass. You see one now, a perfect circle glowing like a ghostly hula hoop in space. That ring is made of a single object's light, smeared out by gravity and curved back into your field of view. You watch it, stunned. The star is behind something massive, yet you see it everywhere. It's not the star that moved, it's the light that did. You shift perspective again, gliding through a galaxy cluster. The combined mass of hundreds of galaxies bends light like hot air above pavement. You see distant galaxies behind it, distorted into arcs and smears. Some are magnified, allowing astronomers to study galaxies that would otherwise be invisible. A cosmic magnifying glass. And then in the dark between galaxies, a stranger feeling, microlensing. This is when a single star or planet passes in front of a more distant star, briefly brightening it by bending its light toward Earth. It's subtle, temporary, and requires tremendous patience to catch, but it's powerful. Microlensing has revealed rogue planets, planets floating through space, unattached to any star, invisible except when they lens the light of something behind them. It's like discovering a wandering ghost by the way it briefly distorts the glow of a street lamp. You glide back now toward a familiar star, its light traveling straight again, uninterrupted, no detours. It's comforting, but you can't unsee it now. Every beam of starlight could be bending. Every twinkle might be warped. Everywhere might actually be a when viewed from the wrong angle. And the bending doesn't just affect light's direction, it affects time. That's the kicker. Time slows in a strong gravitational field. If you could hover just outside a black hole, your clock would tick slower than one far away. Starlight emitted in that slow time environment. It gets redshifted, stretched out not just by motion but by gravity itself. This gravitational redshift was predicted long before we could test it. Now it's measured in labs and in space, all the time. You're not just watching light travel through space. You're watching it travel through warped time. It's all bending, all the time. Your eyes may not see it, but your instruments do. Your models do. Your intuition, now sharpened by this long, slow glide through starlight, begins to feel it. Nothing travels in straight lines anymore. Not in this universe. And somehow, that makes it all the more beautiful. Because even when paths bend, even when timelines warp, even when the light curves around monsters in the dark, it still arrives. It still shines. It still finds you. You coast now toward the star you know best. It doesn't twinkle from your perspective. It doesn't sit quietly in a fixed place in the sky. It blazes, constant, overwhelming, local. You're approaching the sun, not a distant dot of mystery, but a full-blown, blinding beast of plasma and pressure just one astronomical unit away. Your personal daymaker, your inescapable roommate. And yet, you've never really looked at it. Not like this. You hover a safe, metaphorical distance from the sun's surface. Because let's be clear, the photosphere is not something you should attempt to tan beside. The surface temperature is around 5,800 Kelvin, and the closer you get, the more the air turns to ionized gas. It's not really a surface at all, just a layer where the plasma finally becomes transparent enough for light to escape. You see now the textured surface of the sun, bubbling granules, each the size of Texas, churning like a boiling pot of light. Each granule is a convection cell, a bubble of hot gas rising from below, cooling and sinking again. It's silent from where you float, but you know better. The sun sings. Its vibrations ripple through its interior like seismic waves, detectable by instruments on Earth. You've seen sunlight your whole life, but you've never watched it form. You've never followed the photons out of the solar core and across the 93 million miles of space to your skin. Now you have, and now you see more. You drift higher into the chromosphere, a thinner, more chaotic region above the photosphere. Here, spicules rise and fall like red-hot daggers, stabbing into the upper layers. The light here is different, less bright, more ultraviolet, more dangerous. Then you reach the corona. Ah yes, the sun's crown. Ironically, the coolest-looking part is also the hottest, over 1,000,000 degrees Kelvin. Historians still argue why this is. How can the outer atmosphere of the sun be hotter than the surface below it? It's a mystery still under investigation. Maybe it's magnetic reconnection. Maybe it's nanoflares. Maybe the sun is just extra. Whatever the reason, the corona shines mostly in ultraviolet and X-ray light. It's invisible to your eyes, unless there's an eclipse, or unless you're hovering here in your imagination, watching the solar wind stream away in every direction. Here's your fringe fact. Every second, the sun loses about 1.3 million tons of material via the solar wind. That's right. The sun is constantly leaking. Particles stream away, traveling at hundreds of kilometers per second, reaching the edges of the solar system and beyond. Some of that wind reaches Earth, of course. It crashes into our magnetic field, bending and twisting it, triggering geomagnetic storms. When it's strong enough, it can light up the night sky with auroras. Or if it's really strong, fry satellites, confuse pigeons, and cause power grid failures. The sun is not gentle. It is not a warm friend. It is a 4.6 billion-year-old fusion reactor that happens to be just far enough away not to kill you. And yet its light gives life. It drives weather, grows forests, powers solar panels, warms oceans, evolves vision, guides migrations, sets sleep cycles, triggers melatonin. Without the sun, your planet would be a frozen rock within weeks. With it, you get wildflowers and swimming pools and beach vacations and vitamin D and seasonal depression. A mixed bag, sure, but overall a good deal. You watch now as a solar flare erupts, suddenly, violently. A loop of magnetic field lines reconnects, releasing an explosion of energy that leaps off the sun's surface. It blasts plasma into space, maybe a coronal mass ejection, maybe just a really angry puff. The light from that flare, already racing toward Earth, it'll arrive in 8 minutes flat, maybe knock out some radio signals, maybe make a gorgeous aurora show. The particles will take longer, hours or days, but the photons are on their way. Every time you bask in sunlight, you're catching a moment that happened 8 minutes ago. Every shadow you cast is a response to that distant inferno. You never look directly at it, unless you're regretting your life choices. But the sun is always in conversation with you. Your skin knows it. Your eyes know it. Your pineal gland definitely knows it. And so do the plants. You drift down now to Earth, watching leaves drink photons with photosynthetic elegance. One chloroplast at a time, converting light into sugar, into energy, into life. It's easy to forget the starlight you see every day is just as real as the light from Sirius or Vega or Betelgeuse. It's just closer, more personal, more consistent. The sun doesn't twinkle because you're inside its light. The twinkling only happens with distance, out there. Here the light is smooth, familiar, full spectrum, tailored to your biology. Funny thing, your eyes evolved to see the exact range of wavelengths that the sun emits most strongly. That's no accident. You are tuned to your star, your ancestors, your cells, your instincts. They've all grown under this steady golden blaze. And it won't last forever. The sun is middle-aged. It has another 5 billion years or so before it swells into a red giant and consumes the inner planets, Earth included. It will not end in a bang, but in a massive expansion, a final brightening, a shedding of its outer layers. Then it will collapse into a white dwarf, glowing quietly for trillions of years more. But not yet. For now it shines, a main sequence star, stable, steady, the cosmic equivalent of a good 401k. You lie back under its light now, softened by atmosphere scattered into blue and gold. It wraps around trees, cats, sidewalks, windows. It catches in hair. It sneaks through curtains. It warms your face and your floors and your cereal. You're used to it, but never forget it is a star. A star that escaped its own chaos, flung photons into space, and against all odds found its way into your eye. You roll onto your side now, eyes half closed, but there's still one question tugging at you. One little childhood curiosity that never got a satisfying answer. Maybe you asked it once during a backyard stargazing night, or while watching cartoons about astronauts and planets. It's simple, it's innocent, and it still echoes. Why do stars twinkle? You've seen it 1,000 times, points of light flickering in the sky like candles caught in a breeze. Red stars blinking, blue ones dancing. Sometimes you stare long enough and imagine they're winking at you on purpose. But no, they're not the ones doing the moving. You are. Well, your air is. You're looking through an ocean of atmosphere after all. The Earth's thin, squishy, turbulent air is a nightmare for starlight. Every beam that reaches your eye has to pass through about 60 miles of this sloshing soup of gas, temperature shifts, and pressure gradients. And it gets worse the closer a star is to the horizon. Light has to slice through even more atmosphere at a shallower angle, like skipping a stone across the thickest part of the pond. As light travels from space to your eyes, it bends over and over as it hits pockets of different temperatures and densities. These tiny refractive changes distort the path just a little, not enough to stop the photon, but enough to jiggle it. That's what you're seeing. The stars themselves aren't changing. They're still beaming straight and true from light years away, but the path of their light is being wobbled by the atmosphere. It's like watching a spotlight through the bottom of a swimming pool. The light is there. It's steady, but your view is. And now you have a name for it: atmospheric scintillation. Sounds fancy, but really it just means twinkling caused by air. Historians still argue whether ancient cultures understood this effect. Many assumed the stars themselves were flickering, alive maybe, or trying to signal something. Others thought they were divine fires, flaring and dimming based on emotion. Even now, there's a certain poetry to it. That flicker feels alive, and in a way it is, just not in the stars. Here's your quirky bit for tonight. Planets don't twinkle the same way stars do. Why? Because they're not points of light, they're tiny disks. When you look at a star, it's so far away that all its light reaches you in a nearly perfect pinpoint. Even in a telescope, most stars remain dots. But planets are much closer. Their light comes to you in a small, spread-out disk of photons. So when the atmosphere jiggles the image, the wobbles average out. You might still see some shimmer near the horizon, but mostly planets shine with a steady glow. That's why you can tell them apart with the naked eye. The next time you're stargazing, look for the bright, non-twinkling stars. If they're solid, unwavering, and kind of bossy in brightness, that's a planet. Venus is a common one, often the brightest star in the sky. It doesn't twinkle, it glows, smooth and confident, like it knows it's being watched. Jupiter too. Saturn if you're lucky. Mars sometimes flirts with a little twinkle near the horizon, but that's just because it's sulking. You drift now above the atmosphere, leaving behind the turbulent air and stepping into the silence of space. The stars here don't twinkle. They shine with unwavering sharpness, piercing the dark like laser points. From this perspective, the cosmos looks stable, steady, honest. That's why we send telescopes up here. The Hubble Space Telescope, for instance, orbits above Earth's atmosphere precisely to avoid all that pesky shimmer. It sees stars in crisp detail. No flicker, no dancing, just clean, sharp light. When Hubble stares at a point of starlight, it's seeing the truth, unfiltered, unbent, unjiggled. But somehow, when you return to Earth, you miss the twinkle. Because the twinkle isn't a flaw. It's a reminder that you're down here, warm and soft, breathing oxygen and wrapped in gravity. You're part of the atmosphere, part of the mess, part of the story. The stars are ancient and cold, but you're the filter they shine through. You're the turbulence, the shimmer, the life. You lie back now, and the stars above flicker as they always have. Some bounce with red glimmers. Others dance in blue sparks. Some wink like old friends. Some flicker with mischief. You see now how that shimmer is the end of a long journey. Starlight was born in a core of plasma, traveled for millions of years through a stellar interior, escaped into the vacuum, sailed across interstellar space, passed through magnetic fields, dodged dust, and then, in its final few milliseconds, it flickers through your atmosphere. And you notice it. You think it's just twinkling, but it's a reminder of the entire path. And the universe filtered through Earth, through you. And somehow, the flicker makes it more real. One more twist. The very fact that our atmosphere causes stars to twinkle was once a major problem for astronomy. But now, scientists have created adaptive optics, systems that use lasers and mirrors to undo the twinkle in real time. They send a laser into the sky, detect how the atmosphere distorts it, and adjust a telescope's mirror to cancel out the blur. It's like turning off the twinkle switch. And yet, some of us still prefer the sparkle. Because while science might crave a steady view, your sleepy eyes find comfort in the shimmer. It's how you know the stars are still there, still shining, still sending their photons across impossible distances, just to blink in your direction for one brief, soft second. So tonight, let them flicker. Let them dance. Let your atmosphere breathe and blur and shimmer. Because even the distortion is beautiful. And if you blink just right, maybe they'll blink back. You lie there now, eyes gently unfocused, surrounded by the scattered glow of stars. And yet the space between them is so dark, unreasonably dark, suspiciously dark considering just how many stars there are. It almost feels like a cosmic plot hole. Billions of galaxies, each with billions of stars, all supposedly blasting light in every direction for billions of years. And yet, the night sky is still black. Shouldn't it be white? This is the age-old conundrum known as Olbers' paradox, named after the German astronomer Heinrich Olbers, who popularized the question in the 19th century. If the universe is infinite and filled with stars, then every line of sight should eventually hit one. So why isn't the whole sky glowing like the inside of a flashlight? You stare at the stars now, letting this thought sink in. Shouldn't the sky be packed? Shouldn't it be full? Shouldn't every inch of night be blinding? It's not. And the answers are deeper than they first appear. The first fix: the universe isn't infinite in age. It had a beginning. That means light from very distant stars and galaxies hasn't had enough time to reach us yet. Their photons are still en route, hurtling through expanding space like late guests to a very slow party. You look out now, not at the stars, but between them, into the darkness, and you start to see it differently. That blackness isn't empty. It's full of potential. It's full of light that simply hasn't arrived yet. The second fix: expansion. The universe isn't just old, it's growing. And as space stretches, it stretches the light within it. That means visible light from faraway stars gets redshifted into the infrared, microwave, or even radio range. In other words, much of the cosmic light is still out there. It's just invisible to your human eyes. And then the third fix: stars aren't eternal. They're born, they shine, and they die. That means even in an infinite universe, the light-producing members are temporary. There's a natural cap on how much light can be out there at any given time. You hover now at the edge of these ideas, seeing the sky in a new light, pun fully intended. The darkness isn't proof of absence, it's proof of timing, of limits, of the universe's mood swings. Historians still argue whether Albers himself really grasped the full implications of his paradox. He suggested interstellar dust might block the light. But here's the twist: dust absorbs light, yes, but then it heats up and re-emits that energy as infrared radiation. Over time, even blocked light would add up. So no, dust alone isn't the fix. It took a better understanding of cosmic age, relativity, and redshift to really close the case. The darkness is a result of cosmic boundaries, the finite speed of light, the finite lifetime of stars, the expansion of space. Here's your quirky twist: the night sky used to be brighter, not dramatically but slightly. In the early universe, say a few billion years ago, there were more stars packed into tighter space, more galaxies colliding, more fireworks. The universe is gradually dimming. We live in what some call cosmic twilight. Not too early, not too late, just before the big fade. You float now past galaxy clusters that were brighter in their youth, now drifting apart, their light stretching, cooling. The night sky is going to get darker over time. In a few trillion years, if the universe keeps expanding, distant galaxies will redshift so far that they'll be completely invisible. Future civilizations, if any remain, might look up and see only the dim glow of their own galaxy. No others, no clues to the bigger picture. Their sky will be lonelier. And yet you're here now, looking up at a sky full of stars, not full to bursting, but full enough. You float through the void between stars and see just how much isn't glowing. How much is cold gas, dark dust, black holes, voids. Even in galaxies, only a fraction of matter shines. The rest is dim, hidden. And then there's dark matter, not glowing at all, but pulling on the stars through gravity, shaping the universe without so much as a photon to its name. So maybe the dark sky isn't a flaw. Maybe it's part of the balance. Light is precious because darkness exists. Starlight matters because it breaks the void. And the void, it isn't just nothing. It's the space between, the waiting room of the cosmos, the backdrop against which all starlight stands out. You lie back and realize it's not supposed to be all bright. That would be chaos. That would be noise. That would be static. Instead, the stars sparkle in contrast, in context. They are noticed only because the night sky is dark. And that darkness, it's honest. It's the truest proof that the universe has limits, that time matters, that not everything arrives at once, that some things are still on their way. So the next time someone asks, "Why isn't the sky white with starlight?" smile and say, "Because the universe is still speaking. And some of its words haven't reached us yet." You breathe in slowly, maybe without meaning to, maybe because this next stretch of starlight leads inward, not toward a nebula or a galaxy or a photon's infinite commute across the void, but toward yourself. Because tonight you're not just stargazing, you're light catching. And not just any light. You're tuned body and brain to the radiation your own star emits most strongly. That's not poetic metaphor. That's evolution. Your eyes were built for sunlight. Think about it. Out of the entire electromagnetic spectrum, from low-energy radio waves to the searing buzz of gamma rays, you can only detect a sliver, just a narrow band of wavelengths nestled between ultraviolet and infrared, the so-called visible spectrum. But why those wavelengths? Why can you see red but not radar, blue but not Bluetooth? Simple, because those are the wavelengths the sun gives off most intensely. You're not guessing. You're adapted. Every rod and cone in your retinas is fine-tuned to this narrow window of light. The spectrum of starlight shaped your biology. And it's not just you. Moss, coral, cats, crows, trees, they all interact with light differently, but nearly all life on Earth uses sunlight as its starting point. Whether through vision, photosynthesis, warmth, or timekeeping, solar radiation is the metronome of life. Historians still argue whether early biologists truly appreciated just how customized life is to starlight. We now know plants evolved to absorb mostly red and blue light, wavelengths rich in energy but still manageable. Green light, it's actually the part they reflect. That's why leaves are green, because they're too cool to absorb that band. You're floating now in the sunlight spectrum, slowed down and spread out. Red at one end, violet at the other, with familiar names in between. You imagine your eyes rewinding through time, millions of years of slow genetic sculpting, tweaking photoreceptors, refining pigment proteins, until finally, Your ancestors blinked into a sky bright with day and dark with stars. The result, trichromatic vision. Your cones come in 3 flavors: short, medium, and long wavelength detectors. S cones for blue, M cones for green, L cones for red. Together, they let you detect over 1 million hues. More if you count digital filters and a deep love for sunsets. Other animals are different. Some birds and insects have 4 cones, tetrachromatic vision, which means they can see ultraviolet. Flowers evolved to reflect those hidden patterns, invisible to you but screamingly obvious to bees. Snakes detect infrared, sensing warm bodies in the dark. Mantis shrimp, they might have up to 16 photoreceptor types. Scientists still don't know if that means richer color perception or just better bragging rights. But you're tuned to the output of a G-type main sequence star, our Sun. Its radiation peaks around 500 nanometers, right smack in the middle of your visual range. Coincidence? Hardly. You evolved to see what's most available. You evolved to see your star. Here's your quirky detour, deep under the sea, where starlight doesn't reach. Some fish have lost their color vision entirely. Others have invented their own. Certain deep-sea shrimp can detect bioluminescence in ways that make no sense to land dwellers. It's not that there's a right kind of vision. It's that vision reflects the light you live with. Now take that thought and flip it around. Imagine a world orbiting a red dwarf. These stars emit mostly in infrared. A human dropped onto such a planet would struggle to see much at all. But the life there, it would see perfectly. Their eyes, if they have them, might be tuned to longer wavelengths. Maybe they see warmth instead of color. Maybe their sunsets glow deep maroon instead of orange. Maybe to them our star would look blinding, too hot, too harsh, like looking into a welding torch. You lie still now, letting your vision fade a little, your room dim, the hum of ambient light flatten into quiet gray. And you realize something. You don't even see most of the light around you. Not really. Your brain edits constantly, focusing on motion, contrast, shapes. Starlight isn't always a visual experience. It's also a biological one. Your pineal gland regulates melatonin based on light levels. Circadian rhythms, your sleep-wake cycle, are entrained by light. That's why you feel sleepy when it's dark, why blue light from screens can mess with your sleep, why early humans started to associate day with safety and night with mystery. Starlight doesn't just reach your retinas. It reaches your hormones, your habits, your dreams. You are, in a very real way, a light-reactive organism. It's not just about sight. It's about rhythm, about heat, about energy. The photons that leave the sun not only light your day, they warm your skin, power your food chain, keep your oceans liquid, and coax your cells into knowing what time it is. You're solar-powered, period. So lie back now and let that sink in. You are made of atoms forged in stars. You are shaped by the light of your own. You are awake because your star says it's morning. And you'll sleep when it tells you it's night. You blink again, watching the stars overhead, distant, untouchable, mysterious. And yet somehow they've touched you, shaped you, defined the range of your senses. You don't just see stars. You are one. Just slower, cooler, sleepier. You lie back now with a new kind of curiosity curling in your chest, not just about stars themselves, but about how we measure them. How do we know how far away they are? How bright? How big? The truth is, when it comes to starlight, we're always playing detective. No ruler, no road trip, just light pure, persistent, revealing more than it should. And that's where the real magic lies, in how we measure the unreachable. You begin with brightness. Seems simple, right? You look at a star, it's bright. You look at another, it's dimmer. That must mean one is closer or bigger or hotter, but it's never that simple. You've got two kinds of brightness to worry about. Apparent brightness, how bright a star looks from Earth. Absolute brightness, how bright a star actually is, regardless of distance. The trick is separating the two, because a nearby candle can outshine a distant bonfire if you're close enough to it. So how do astronomers figure it out? With distance. And for nearby stars, the gold standard is parallax. You hover now beside Earth in its orbit. Wait 6 months. Earth swings to the opposite side of the Sun. From here, the position of a nearby star appears to shift ever so slightly against the backdrop of more distant stars. That tiny shift, measured in fractions of an arcsecond, is the parallax angle. Simple geometry does the rest. The baseline is Earth's orbital diameter. The angle is measured. From that, astronomers calculate the distance. 1 parsec is the distance at which a star shows a parallax angle of 1 arcsecond. That's about 3.26 light years. Yes, parsec isn't just a made-up sci-fi word. It's real, and it's grounded in trig. Parallax works beautifully for nearby stars, but as you look farther out, the angles shrink. After a few thousand light years, the shifts become microscopic. At some point, even our best instruments can't resolve them. So we turn to standard candles. These are astronomical objects whose intrinsic brightness is known, things that act like well-labeled light bulbs. One of the most famous, Cepheid variables. Remember them, the stars that pulse. Their pulsing period is directly related to their luminosity. Measure the period and you know the brightness. Compare that to how bright it looks and voila, you've got the distance. You drift now past a Cepheid in a nearby galaxy. It pulses like a heartbeat, steady, patient. You can see how ancient astronomers, even with primitive tools, could map vast regions of space using just these stellar beacons. Historians still argue whether Hubble's early distance measurements using Cepheids were accurate. He underestimated the distances to some galaxies because he didn't yet know there were two kinds of Cepheid variables. But his mistake still led to the biggest breakthrough of all, the realization that galaxies are moving away from us. The universe is expanding. So, ironically, his measuring errors helped stretch our concept of space. Now you're getting into deeper territory. You follow beams of light from distant galaxies, redshifted, faded, but still readable. For these distant reaches, astronomers use Type Ia supernovae, standard candles of a different breed. These supernovae always explode with roughly the same luminosity. If you spot one in a galaxy, you can measure the apparent brightness, calculate its distance, and add a new data point to your cosmic map. But brightness and distance are only part of the story. How about size? Well, we can't exactly wrap a tape measure around a star, but we can use its spectrum to estimate temperature and combine that with luminosity to estimate size. A hotter star emits more light per square meter, so if it's bright and cool, it must be enormous. If it's bright and hot, maybe it's just closer. This kind of deduction, mixing color, temperature, and brightness, is how we place stars on the Hertzsprung-Russell diagram. It's a plot of luminosity versus temperature, and it reveals where a star sits in its life cycle. Main sequence, giant, dwarf, or somewhere in between. And now for your fringe fact. A new technique called asterosismology. Yes, it's a real word. Lets astronomers study internal star structures by analyzing surface oscillations. Just like geologists use earthquakes to study Earth's interior, astrophysicists use stellar quakes to study star cores. Even light itself, its slight flickers, its frequency modulations, can be used to probe a star's inner workings. You coast past the Gaia spacecraft now, a mission quietly mapping over 1 billion stars in our galaxy with unparalleled precision. It uses parallax to determine distances, proper motion to measure how stars move, and photometry to gather spectral data. It's building a 3D map of the Milky Way, a star chart not just of where things are, but of where they're going. You drift alongside a stream of data flowing from Gaia to Earth, coordinates, brightness, velocities. Every photon captured is a measurement. Every starlight sample, a data point. Even with all this technology, starlight still has the final say. Every measurement comes down to how bright, how shifted, how stretched. You lie back and feel the absurd elegance of it. From one tiny dot of light in the sky, you can learn its distance, its size, its temperature, its chemical composition, its age, its motion, its past, its future, all without leaving your blanket. Starlight is not just information, it's everything. And the way you measure it is with patience, curiosity, and a deep respect for geometry. Because even across billions of miles, even after millions of years, even stretched and scattered and filtered by atmosphere, light tells the truth. You just have to know how to listen. You float now with a smile tugging at the corner of your mouth, not because of some profound cosmic epiphany, but because the universe has a sense of humor, or at least people do. And when it comes to starlight, not every flicker is a supernova or a noble hydrogen signature. Sometimes it's, well, weird. Sometimes it's lasers. You glide through the dark now, not toward a natural light source, but something artificial, something structured, something possibly, just maybe, intentional. Because tonight, you're entertaining the idea that not all starlight comes from stars. Welcome to the speculative edge of astrophysics, where starlight and science fiction hold hands and whisper about aliens. Not the green ones, not the ones with catchy anthems, just the theoretical ones, sending out pulses of light across the galaxy like a cosmic version of tapping a flashlight in Morse code. This is the world of SETI, the search for extraterrestrial intelligence. And while radio waves have long been the go-to signal for hunting alien civilizations, more and more scientists have turned their gaze toward lasers. Yes, lasers, as in highly focused monochromatic beams of light, perfect for long-distance signaling, unmistakable, precise, energy efficient. In theory, if a distant civilization wanted to get our attention and had advanced optics, they might use lasers to do it. And how would we detect that? Starlight doesn't flash. Not like that. Stars don't emit tight, rapid pulses of identical frequency. If you're watching a star and suddenly detect a nanosecond-long burst of identical photons, all in the same wavelength, with no known natural cause, that's not starlight. That's something else. You hover now above Earth, where observatories like the Breakthrough Listen Initiative scan for precisely this kind of signal, sifting through terabytes of light data, looking for laser pulses, unnatural periodicities, or anything that breaks the quiet background rhythm of natural radiation. Here's your fringe fact. In 2015, astronomers detected a bizarre, rapid dimming of a star known as Tabby's star, KIC 8,462,852 if you're into catalog numbers. The starlight dropped in irregular, asymmetric patterns, not like an exoplanet transit, not like dust. And for a while, the internet exploded with speculation. Was it a megastructure, a massive alien array, a Dyson swarm harvesting stellar energy? Probably not. Later studies pointed toward dust and comet fragments. Still, no one's fully settled the case. Historians still argue whether it was a publicity stunt or a genuine moment of scientific curiosity. But what mattered was this. For a brief moment, starlight carried the weight of possibility. That's all it takes. One strange flicker, one unexplained dip, one spectral anomaly that doesn't line up with anything we know. That's the bait, the invitation, the breadcrumb trail. You drift now alongside a photon that could be artificial, could be a laser sent by a planet 1,200 light-years away. It might be a misfire, a calibration beam, or a cosmic lighthouse. Or it might be nothing. That's the thing. So far, we've found no confirmed signals, no starlight that winks in prime numbers, no flashes that repeat with purpose, no carrier beam holding galactic Spotify recommendations. But we keep watching. Because the sky is big, really big, and lasers, focused as they are, might only hit us by accident or once, or never again. As still we look. And sometimes we send signals too, radio pulses, mathematical sequences, light beams just in case. And if they exist, and if they're watching us, they might see our sun dim just a little as Earth passes in front of it, just like we detect exoplanets. They might notice the oxygen and methane in our atmosphere, clues of biology. They might notice the broadband radio leakage, the satellites, the streetlights. Our starlight, reflected, pulsed, diffused, might be reaching them now. Right now, as you lie in your room, blinking in the faint hum of LEDs, your planet glows subtly in the dark. A pale blue dot, giving off just enough light to be seen. It's humbling. Because even if we never receive a laser beam from another world, we've already become one. Earth is a starlight anomaly, a flicker of life in the void. You hover now between stars, imagining how many others might shine like ours, not in brightness, but in complexity, in chaos, in biology. There are likely billions of Earth-like planets in the Milky Way. If even a tiny fraction hold life, and an even tinier fraction evolved intelligence, and one decided to aim a beam of light our way, would we notice? Would we be ready? You think again about that laser, a sharp line of light crossing centuries of space, finally striking a telescope, bouncing into a sensor, triggering a data flag. And then what? A single pixel of brightness, a lone ping. Would we even recognize it for what it was? That's the mystery. We're good at detecting natural light, but intentional light, that's harder. There are no road signs in the cosmos, just flashes and hope. So you lie back, eyes unfocused, wondering, has starlight ever lied to us? Or have we just not asked the right questions yet? Because sometimes the most extraordinary messages don't come in words at all. Just light. Perfect, focused, unnatural, waiting to be noticed. And now, at last, you drift toward the edge, not of the universe, but of its light. Because even though stars seem eternal, even though their glow defines night and rhythm and curiosity, all starlight has an expiration date, a final destination, a dimming point, a curtain call. You've spent this whole journey tracing light, through birth in stellar cores, through the crowded escape from plasma prisons, across time and space and gravitational bends. You've chased flickers and ghosts, rainbows and whispers. But tonight, you follow it one last time, all the way to where the starlight ends, where it fades. It begins with the stars themselves. They don't last forever. Each one is powered by fusion, by burning hydrogen into helium, then helium into heavier elements. But that fuel runs out, always. The more massive the star, the faster it burns. The big ones, they live for millions of years, short lives, loud endings. The small ones, red dwarfs, can live for trillions of years, sipping fuel slowly, barely glowing. And when even those are gone, only the embers remain. White dwarfs, cooling slowly, glowing dimly in infrared. Eventually, they'll fade too, becoming black dwarfs, theorized objects that no longer emit any light at all, just cold cinders, fossils of former stars. No black dwarfs exist yet because the universe isn't old enough. But one day, trillions of years from now, the last stars will flicker out and the cosmos will go dark. The end of starlight. Historians still argue how long this future dark era might last. Some models predict the last light will come from occasional white dwarf collisions. Others suggest even those will cease. There'll be no more fusion, no more light, only decay, only gravity, and black holes. You float now in a projected future far beyond human timelines. No stars, no planets, just dark matter, black holes, and the stretched remains of a universe cooling toward absolute zero. The last photons here are whispers, cosmic microwave background radiation, redshifted into meaninglessness. Starlight, once everywhere, is now a rumor. Even black holes will vanish eventually. Through Hawking radiation, they will slowly lose mass, emitting the tiniest trickle of energy until they pop out of existence. And then nothing radiates. Not light, not heat, not sound. Just the void. This is what physicists sometimes call heat death. Not because it's hot, but because all usable energy has been spent. No gradients, no thermodynamic differences, just stillness. The universe dark and quiet. You might think this is a sad ending. The lights go out, the show's over. But not quite. Because even in this far future, light is still preserved, not in the sky, but in the places it touched, in the things it built, in the atoms it forged. Your bones, formed from elements born in stars. Your thoughts, made possible by neurons that fire thanks to sunlight harvested by plants. Your memories, bathed in the light of a middle-aged G-type star, just the right size, just the right distance, in just the right arm of a spiraling galaxy. You were part of starlight's golden age. Here's your quirky final fact. We already harvest ancient light, not from stars, but from objects billions of light years away, galaxies whose photons began their journey when Earth was still forming. We see their past, always the past. So technically, the night sky is already gone. The stars you see tonight may not even be there anymore. Their light is late, beautifully, hopelessly, perfectly late. You lie back and take it all in. The sky above you isn't full, but it's enough. Enough to tell you how stars are born, how they shine, what they're made of, how they flicker, fail, explode, and fade. Enough to help you measure the immeasurable, to wonder about neighbors, to ponder the dark. Because in the end, the universe is not about the light that's still coming. It's about what the light has already built, the story it has already told. And as you blink slowly, letting your breathing soften and your thoughts drift, you realize that even if starlight ends, the seeing never does. Because you are the creature who noticed, who listened, who asked. And that makes the dark a little less lonely. And now you're still, floating not just through space but through silence. No more flickering flares, no bursting novas or whispering photons. Just you, the memory of light, and a night so quiet you can almost hear the universe exhale. You let your thoughts settle like dust on a windowsill, slow, gentle, without needing to be gathered up or understood. The stars you've traveled to and from, those ancient fires, are behind you now. You're not chasing their light anymore. You're resting in it, letting the warmth fade to a soft afterglow that sinks into your skin like the last breath of sunlight before evening takes over. No more questions, no more measurements, no more spectral lines or redshifts or orbits or parallax. Just stillness. You feel, maybe for the first time, how long starlight takes to arrive, and how short a moment it stays with you. It brushes your eyes, your mind, your cells, then keeps going. Into you, through you, beyond you. And that's all it ever needed to do. Let your shoulders drop now. Let your chest rise and fall on its own. The room is dim. The night is full, and nothing more is required of you. It's not even wonder. You've done the work of dreaming, of asking, of letting your mind drift into the dark and come back with something quiet and beautiful. So now let it go. Let the stars turn into shadows. Let your breath slow to match the hush of a sky with no questions left to answer. You are safe here. You are small, and that is a kindness. There is no light to follow now. Only rest. Only dark. Only sleep.